Alright, hell yeah. So we got material mechanics and we got a 2-star problem. And you know what I mean? It's late at night. I probably shouldn't be starting this, but I want to try to get some of these problems done in a reasonable amount of time. So let's read this one. So we have 2 cables, cool, each having a length L, approximately 40 meters, blah, blah, blah. Supports a container that weighs W. The cables have an effective cross-sectional area, cool, 48 millimeters squared. Just divide by 10 to the 6 to make that meter squared. Cool, we'll do that later. And a modulus of elasticity of the steel cables, 160 GPa, gigapascals, and that's pretty close because typically it's typically it's 200 gigapascals for steel, but steel cables will stretch more. That means this number is going to be lower. The higher this is kind of modulus of stiffness. Higher the number, kind of the stiffer, less elastic. Anyway, okay. And they're identical except that one cable is longer than the other. When they are hanging separately and unloaded, the difference in length is 100 millimeters. Cool. And the cables, so that's going to be 0.1 meter. Cool. Keep that in mind. 40 meters total length for this length. All right. The cables are made of steel having an elastoplastic strain diagram with the yield. So kind of we use this as strength. So like the max strength is going to be 500 megapascals. And that's going to be a pretty high number, especially for steel. For weldable steel, this is 400. And this is 200. So rigid and not as strong. But steel cables can be probably even stronger than this. But this is going to be a higher number, 500 megapascals. And definitely more elastic. So assuming that the weight W is initially 0 and slowly increased by the addition of the material, assuming that the weight W is initially 0 and is slowly increased by the addition of material, to the container. So this is a container that's going to be filled with stuff. You know, and this is just real life. You know what I mean? You have 2 ropes that are trying to hold up a container, and guess what? One is a little bit slack. So, and guess what? You've already said maybe that, so in this case, you're going, like one of the cables is going to take all the weight. And let's say, and so this problem just right off the bat screams like, okay, so can a 40-foot length cable, and let's do this. You know, let's say your length is 40 meters. What do we know about typical steel? Steel is a stretch of 0.002. This is called strain, but it's going to be 0.002. So our equations for steel, our strength is equal to force over area. Our stretch is change in length divided by total length. So now we can rearrange this equation to find change in length max. Well, I mean, well, we can just guess. We can just say this is steel, but we know we can solve for this value just in a second. But let's just throw it in to get a ballpark. So we're gonna find L is gonna go upstairs. So you're gonna go this EL, and you're gonna get 0.002 times 40, and we probably do this in our head. Is going to be 8. So you're gonna have 0.08, and that's going to be meters. And that's going to be 80 millimeters. So even just right there, no. One of these cables, well, let's actually do it for real. Because the other equation that we need, these are the first 2 that you want to write down. And then the third one relates, you know what I mean, measurable, measurable strength to change in length. This is a ruler. And that equation is going to be strength is equal to stretch times modulus of elasticity. Stress is equal to strain times modulus of elasticity. So put these equations together, F divided by A, and then change in length divided by L. So you got F divided by A is change in length divided by L times modulus of elasticity. And, whoa, hold up. No. We already just want this. So here, so any subscripts that we put on this, so we could say, hey, max strength is equal to max strain times modulus of elasticity. E is a constant, doesn't change, but the subscripts on these have to match. So we're going to go yield. It's pretty close to the max. I mean, it's elastoplastic, so it is max, you know what I mean? because you have a graph like this. This is your yield, and in an elastoplastic problem, we're not doing any of that. We're just saying, hey, cutting it off, and the graph goes this way and then that way. So the material can lengthen more, and it can take this much stress, so it can take the same force until it does break eventually. Yeah, and then just keep in mind that the strain here is going to be something like 0.002, but out here it could be up to 5%, so that strain would be 0.05, you know what I mean? So those numbers. And this becomes 5% and this becomes 0.2%. Okay, so now we have kind of a general gist of how elastoplastic materials work, and we can put this in. So strain yield is equal to E, and then we can rearrange. You know, we know E from our problem, and we know yield, so we just rearrange and get that. So we get yield strain is equal to, and if you don't like this, you know, so far you could also be like, hey, I don't want to solve for yield strain and then say yield strain is change in length divided by length. I just want to find that change in length. So I'm going to go yield stress is equal to change in length due to yield divided by the total length E. So some parameters don't change. Whatever your A is, we've already established that. Whatever your length is, we've already established that. So these are established length. These are the variables that can change. So we'll rearrange for this, and we'll go change in length due to yield. L goes upstairs, is stress yield length divided by E, and now we're just money. So we're going to go 160. Change this to pascals or Newton meters. So 160 times 10 to the 9 Newton meters squared. Length is 40 meters. And then E is 500 megapascals. So it's only 10 to the 6. So get used to this. This G is 10 to the 9. This M is 10 to the 6. All right. And, you know, 10 to the 6. This is going to be 10 to the 3 at the end of the day. And what else could we do? We could just guess. This is pretty close to 500. So we're basically going to have 500 divided by 500 is going to be 1. So essentially we're going to have a change in length of 10 to the 3. That makes no sense. No, I messed these up. Yep, so I already caught my error. So yield stress is the 500 up top. 500 times 10 to the 6 Newton meters squared. Length is 40. That was a good check. Anytime you're working with big numbers, do the, you know, just kind of guesstimate. And 160 times 10 to the 9. Now 10 to the 6. Now we're going to be left with 10 to the 3 downstairs, and you're going to have 2,000 divided by 100. You know what I mean? Or 2,000 divided by 200. So you're going to be left with 10 up top, 10 to the 1, divided by 10 to the 3. So you're going to have something like 10 to the negative 2, which is 0.01. And that's going to be 10, that's going to be 0.01 millimeters, 1, 2, 3. That's going to be, is it 10 millimeters? Oh, man. I don't know. I think I'm off by a factor of something. But in our calculator, I'm going to go E 160 times 10 to the 9. I'm going to store that as alpha E. Sigma, I'm going to do alpha O, you know what I mean? But 500 times 10 to the 6, stored as alpha O. And hell, let's try this. So alpha O, and then L. So 40 stored as alpha L. So we're going to go alpha O, alpha L, divided by alpha E. And we get, yeah, that's why I was off by, yeah, I don't know how I messed that up. Could I figure that out? 2,000. Oh, see, this isn't 2,000. I always mess this up. 5 times 4 is 20, and then you got 1, 2, 3 zeros. So this is 20,000. And so my 0.01 estimate goes to 0.1 meters, and I got 100 millimeters. And then our problem says that this is 0.125 meters, which is 125 millimeters. So even just right now, we know that when our cable is fully maxed out on this elastic, it can stretch 125 millimeters, but after that it can't stretch anymore. Once it's past 125 millimeters, it's permanently going to deform the cable. All right, hell yeah. Okay, cool. And then even just right there, so we kind of guesstimated and then threw in the numbers, and we get that one of these ropes can stretch 125. And then we know that there's slack. We know that there's slack of 100 millimeters in one of the cable. So by the time one of the cables gets to be maxed out and is going to start to plastically stretch, the other cable is going to see 25 millimeters of elastic travel up this. So we say right here is 125 millimeters, and so you have this elastic scale. So the other one's going to see 20. So you're going to have divide this up into 5 chunks, and the other cable is going to be right up to there. So let's see what the question says. Determine the weight YW that the first produces yielding of the shorter cable. So that weight, and see, if you just had one cable, you know what I mean, that would be fairly easy. You would say that because your equations are these. So let's rewrite the equations. Strength, force divided by area. Stretch is change in length divided by length. Strength is EE. And then you can rearrange these equations. I just kick them out. I know that these are the equations that I want. Change in length is FL over EA. And then I also want force is equal to, bring the EA upstairs, change in length EA divided by L. And I do write it like this. I shouldn't write it like this. I should get used to writing this like force is equal to EA divided by L change in length, because the force of a spring is K change in length, and that's exactly what this is. This is K. So this is force K change in length. All right, hell yeah. Because it says, you know, if you EA divided by L, these are all given parameters. We've already made the cable. So A and L are like what you made the stuff out of. We already established that we have a 40-meter cable, and then we have a cross-sectional area of A, and then we have a material that has a property that relates these two things, stretch and breaking force. So these two things basically relate force that you can put on something, the poundage, and then the change in length that you can observe before breakage. You know what I mean? Those are the two things. Pounds to break, and then elongation to break. They're just wrapped up into geometric properties that don't change, but you do get PSI out of this, which is useful, and you get a dimensionless parameter that's probably confusing as all hell. All right, so there you go. If we just had one cable, so any of these, put subscripts on. See how I already said that these do not change? So now I can say, like, we can put a subscript on that. Force max is change in length max, EA divided by L. And then how the hell did we find change in length over here? Well, we basically took these first ones and said strength yield, which is the same thing as saying, hey, max, kind of the max strength we can get out of it is the max strain times E. This is kind of makes more sense, you know what I mean? And we found the max strain, or we should, is equal to max strength divided by E, and we're just going to say that's the yield divided by E, which is, so we're gonna plug and chug this. 500 times 10 to the 6. This is Newton meter squared. That's pascals divided by E, which is 160 times 10 to the 9 Newton meter squared. So let's store this. We'll store this parameter as Z in our calculator, and that'll be the max strain. So we got alpha O divided by alpha E, and we're going to store that as alpha Z. But see how this number is just crappy and it's small? But it's relatable, 0.003125. Like I said, steel, weldable steel is 0.002. This is going to have more stretch. It's going to have more change in length per length, because that's the value on this. And now we can find, you know what I mean? Now we're going to say, hey, strain max is equal to change in length max divided by L. That's the definition of stretch. Stretch is change in length divided by total length. So we're going to rearrange this and solve for change in length max is strain max times length, and that's going to be that Z, this number, times 40. And literally we already did this, we're just literally doing it twice, and that's why my videos are hella long. And we get 0.125 meters, which is 125 millimeters. Cool, we already figured that out, but we just kind of want to visually see that, where that came from. Because now we just know that this is our max length, change in length, before things go plastic, put it that way. Alright, so we're going to say if we just had one cable, our max force is going to be a lot of different ways you could solve that, but it's just going to be our max length times EA over L. So we can plug and chug on that, and let's just do that right now. I'm going to store this as X. So our max length, change in length, is X. So we're going to go X alpha E, and I got to get this in for A. This is 40 divided by 10 to the 6, and that's going to store it as A. So yeah, that's going to be area is 4.8 times 10 to the negative 5 meters. And here we go. We got X alpha E alpha A divided by that 40L. And we get a force max, and we're going to store that as F. And we get 57,897. And we kind of know something about steel, is that steel can get about 58,000 pounds per square inch. So is 48 millimeters squared about 1 square inch? We can square root this, square root of 48, and that's going to be 6.9 millimeters. And we can see that, you know what I mean, if this was a square, we would have 6.9 by 6.9, and 6.9 divided by 25.4 is 0.27. So it's going to be about a quarter inch times a quarter inch. So no, this thing is square that. This thing does not. This thing has a very small area, but that's interesting. The force max, it's pretty darn strong. It's stronger than normal steel, that's for sure. Okay, so now what the hell? Let's see. So yeah, so we found the max force that one of the cables can take. But here's the deal. This is why this makes this a 2-star problem. It's kind of like a head scratcher. It says determine the weight that you put in this thing that first produces yielding of the shorter cable. Well, if you just had one cable, this would produce yielding of the shorter cable. But guess what? You would have to stretch this 125 millimeters. But when you stretch it 100 millimeters, so let's put that in. So let's put 100 millimeters in here, and we're going to go 0.1 times alpha E alpha A divided by alpha L. Store that as G. So this is only going to be 19,200. How the hell? No, you know what I mean? I threw in the wrong value. Or actually, no, this number was way the hell wrong. I'm glad I did a check on reality, because I was just like, this thing is not an inch squared. I just threw in the wrong value for X. So 0.125 stored as X, and now we can, you know, friggin' A, do that. So this will give us the right answer. And if we did stretch one cable 125 millimeters, we would get a force stored as F of 24,000 newtons. It's not even pounds. And I don't even know why I thought that was pounds. That was crazy. We're all in metric. This is 24,000 newtons divided by 4.44. It's 5,500 pounds. Cool. And yeah, we got a quarter-inch cable, basically. 2 quarter-inch cables that are pretty damn strong. All right, cool. And if we just had one, so if we just stretched one cable to 100 millimeters and the other cable's still slack, it ain't taking no weight, we could put 19,200 newtons because we threw in 100 millimeters, 0.1 meters in this one. Okay, but the second both cables then lengthen another change in length of 25 millimeters, well, you know what I mean? They're just springs, you know what I mean? So at the end of the day, force is K change in length. All right, hell yeah. So yeah, these cables are just springs where they follow this equation. So if you change their length by 0.025 meters, which is 25 millimeters, you know what I mean? You're going to pop out a force. But see how this is just a linear relationship? I mean, if you, so, and it doesn't matter if one cable is already stretched. If you have a spring like this that's unstressed, and then you're going to move it an inch. Okay, cool. It's going to take, let's say, 10 pounds. Well, let's say you come across a string that's already stretched by 10 pounds, and you want to stretch it another inch. Cool. Guess how much that's going to take? It's going to take another 10 pounds. You know what I mean? Just that is not intuitive, though. It seems like a spring is going to be harder to pull once you pull it more. But that's not the case. But it is the case if that spring gets so sprung that now you're just pulling a length of steel. Well, that's exactly what's happened. It's like, hey, you have a spring that can be pulled apart, but once it gets to here, it's like just like pulling. Well, that's a bad example. Because you can put more resistance in the spring, but then all of a sudden the spring just starts to give away. So yeah, that was a weird one. That was a weird example. But anyway, okay. So now, so we know that one cable can take 100 millimeters of stretch and take this 19,200 newtons. I'm going to store that as G. So we got that, and then when we stretch the cable that extra 25 millimeters or 0.025 meters till that first cable, that's what it asks. When that first cable produces yielding, what's the force? Well, each of those cables is going to have to take the 25. So we're going to say force in cable 1 is K times that change in length, 0.025. Force in cable 2 is K times 0.025. Guess what? Force is equal to EA divided by L. You just have this kind of memorized because, hell, that's K. And what is K? It's a function of a constant and then the area that we chose and the length. Both these are identical. So K is going to be identical for both of them. But let's just solve it for one, just so we don't get messed up. Because for that new cable to stretch 25 millimeters, its force is equal to EA divided by L times times that change in length, 0.025. Cool, let's do that. Alpha E, alpha A times 0.025 divided by alpha L. So that's 4,800 newtons stored as alpha H. Cool, but now let's say the other cable has to go from 100 millimeters to 125 millimeters. You know what I mean? No, I was... Well, am I wrong on this? I don't think so. So let's do it two ways. We're kind of running out of juice here. But let's say we said F is equal to K times 0.125. And then we're going to find this. We already did. That was, we already did. So that was F. So this was stored in our calculator as F. This was at 125 millimeters. This is at 100. So the difference between them is the force required to pump it up. And it should be 4,800, right? I mean, after I said all that, minus 1920. And yeah, it's 4,800. So that kind of proves it. And I'm glad we don't have to kind of switch papers or write real tiny. So there you go. So the weight that it produces yielding in the first cable is hell. Change the length by 100 millimeters. So the other cable is still slack, and you get G. And then add this twice. So we're going to add H times 2 plus alpha G. So you're going to get 28,800 newtons. And I'm going to store that as alpha I. Hell yeah. And then the next problem, it says determine the weight P that produces yielding of both cables. Okay, So this is kind of fascinating, because once the first cable yields, we've already established that was this first one, F, that we did. And I'm glad we did that. We said the first cable, if there was just one cable, it can stretch 125 millimeters. It'll act like a spring till it gets to that point and can take a force of 24,000 newtons. And this is 20, so this is synonymous, because F over area is the stress, but the area is all the same. But the force right here is 24,000 newtons. And then as it elongates more, it's still holding a force of 24,000 newtons. It can't take more force because that force is already in there. So it's just going to hold 24,000, but no more. No more. You know what I mean? And but the other cable can still stretch from the point that we found another 100 millimeters. So we can go F times K times 0.1 of the other cable. Well, this is so dumb. Determine the weight P that produces yielding of both cables. Well, no duh, no duh. The one cable can only take 24. The second it starts to elongate more, it can't take more. And guess what? Well, what do you think the other cable can take? The other cable can stretch that full change in length max, and it can only change in length by 24,000. So that's just meant. So some of these the elastoplastic problems of everything fully reaching its plastic is just reaching its max, and that's going to be real intuitive. So that's just going to be 48,000 newtons. So there you go. And now it says construct a load displacement diagram showing the weight as ordinate. That just means on the x-axis. Well, I forget. I looked it up. For the love of God, why don't you usually, no, that's the y-axis. So it's usually going to be weight up here and then delta down there. And then do that. But I mean, you could do that. I think just even that's probably the hardest part of this. It's not very hard at all, because you're going to have linearly and we can do that. So, but yeah, that's we might as well check the answers in the back of the book if it was that easy. But these plasticity problems or elastoplastic problems, like one answer is always super straightforward, and I don't know. They don't have to be super complex problems. I just say, hey, just figure out if it's just one. But there you go. So you have 28,800, and it's in kilonewtons. I don't know why I messed up on the kilonewton part. That's a bummer. And then we have 48. Oh no, I didn't mess up. It's 28.8. So that's 28,800 newtons, and then 48,000 newtons. And that's exactly what we got, right? We said it's G, alpha G plus 2 alpha H's. Yeah, 28.8. So super easy. And we can even, you know what I mean? We got some minutes to do this. So we'll do a little diagram. Like we said, for that first 100, 1, 2, 3, 4, there you go. For that first 100, it's only going to be one cable. And so that one cable is going to stretch 19. So we're going to go probably like 1, 2, 3. So this is going to be 30 kilonewtons. Well, I don't know, 10,000, 20,000, and then 30,000. And then we got 5, 5, 5, and then maybe 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Hell yeah. Alright, so now we really can do this. So we have at 100 millimeters, it's going to be 19. So we're going to go boop-de-scoop-de all the way up to 19. So right there, 19.2. And then what else? So then you're going to get the other one. So this is going to be a linear relationship with one, and then you're just going to go straight for where they both fully stretch out. So that's going to, if you can get 100 millimeters out of one cable, because these things, the cables have a slack of 100 millimeters. So obviously, one cable can take this full stress before the other one, All right, hell yeah. So yeah, we're home stretch on this. So yeah, at 100 millimeters, the other cable still is taking no force. Force is still 0. It's just right at the end of slack. But now the other cable is going to can stretch out, and it can stretch out. I mean, we already figured that max change in length is 125 millimeters, and so now you're going to go 1, 2, 3, 4, 5. And so now you're going to go 200, and then here's 100. Here's 225. So at this point, then they're both going to be stretched out. Oh, and I made my graph horrid because it's going to be 48,000. So oh shoot, damn it, it's not going to be to scale. So we're going to go 40 and then 48 right there. So this is 4,000, and this is going to be 48,000. So there you go. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so then this other point's going to be right there. So and it should be just a touch higher. But then from here, you're going to go. We should do this so it's not just a. Damn it. Well, let's try again. So we're going to go 1, 2, 3, 4, 5. And now over here we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, I think. And then, so here's 1, 2, 3, 4. This is 100. 1, 2, 3, 4. This is 200, and this is 225. This is that 4,800. So we're going to go right up to there. And this is 100, and then this is 20. What was it? It was 19. So right at 100, you're going to go right to here to 19.2. So there you go. Now you can see the difference. So you definitely, and this makes sense. This shows the load weight. So with just a little bit of weight, this thing's stretching out hella. Now double that weight, and it didn't stretch out as far. See how this is hella? And then this ain't as far, and you increase the load. Okay, but then you increase the load till they both go plastic. Now what? This is the most important part of this. Oh yeah, it's just that way. And it's significant, you know what I mean? If you, like, I want to go to the hardware store and start reefing on bolts, because the second they stretch out past their elasticity, you know what I mean? They don't go back to the normal shape. But once you do that, you know that you're putting a constant force into that bolt. You know what I mean? So it's just fascinating. And if you know the material properties of that bolt, you can kind of tell the force that you're putting into it. So this is going to be 48,000 newtons. And again, to make this make sense, you know what I mean? To put a full perspective on it, we said that strength is equal to EE. And then we rearranged, and we said, hey, max is equal to strain max times EE is the constant. Let's rearrange for max. So this max is equal to stress max divided by E, and we just did that. That's alpha O. I mean, it's in my calculator as, well, I thought it was alpha Z. Yeah, it's in my calculator as alpha Z, this term. But it's alpha O divided by alpha E, and that's Z. And this term is 0.003125. And as a percent, times 100%, this is 0.3125% of the total length. Well, what the hell do we know about steel? We know that steel can for sure elongate 5%. Some specimens of steel can elongate up to 30%. You know what I mean? So they have a plastic range. Now, if you're elongating more than this number, you're probably going to kill people. You know, if you're designing things, you just have to stay within, like, everything on this side is your factor of safety. Land right there. Never land out here. But this is that classic case where it's just like, well, this is a determinate structure, and you have two cables to take the force, and it's gonna be okay if one cable stretches. You know what I mean? Just because you get into a plastic range doesn't mean like that you've permanently effed the cable. You know what I mean? Some things are designed this way, but definitely not bridges and structures. Because what, let's see, how can I word this? Oh shoot. Oh yeah, it goes back to how much can you stretch something. Like this is so minuscule. We're going to show how ridiculously minuscule this is. Because even that 125 millimeters right here, oh, and did we do this hella wrong? I think we did. Yeah, no, we did this hella wrong. Yeah, no, I mean, no, we didn't do it hella wrong. But, your points are going to be 19, but at that 125 millimeters, you're going to go up to 28. So here you go, 1, 2, 28. You're going to be up to here. So you're going to have two different curves. You're going to go here to here, and then you're going to have kind of a steeper stretch, and then from here to here, you're going to have a more mellow. So let's talk about it. Yeah, I'm so glad I did this, because that first cable is the only one that's doing crap. You know what I mean? So it is stretching out quite a bit. But then both cables are hooking it up. But once you get to here, this cable can only... Like if you just had this cable in a graph, it would look like that up to 125, and then it would flatline. It can't take any more than 24,000. So the second this can only take, it can't take no more. Now this cable is the same slope as this cable. So that's what they want you to know at the end of the day. The slope of this is the same thing as the slope of this. And then once this cable flatlines, hell yeah, like you got issues. Like not only is it going to stretch out, if you put 50,000 newtons, well, it's going to stretch, but it can't hold that extra 22,000 newtons. It'll just stretch till it breaks. You know what I mean? Where here you have a cable that is stretching to its plastic load, but then it's backed up by something that's elastic. You know what I mean? And then you don't want to pass that point. But it's okay to be in this range with this design. Stuff like this gets designed all the time where one member hits its plastic point. Let's get some more light. Okay, but the take-home message is going to be pretty cool on this one. It's going to show you that 125 millimeters is potatoes compared to... So if you have something that's 40 meters, and I say it can stretch a max of 5% before like crap hits the fan. So we're going to go 40 times 0.05. That's how you do 5%, because 5 divided by 100, that's the ratio. 5 divided by 100 is 0.05. That's what we multiply by 40. And you got 2 meters. This cable can stretch 2 meters. That's 2,000 millimeters, I'm sorry. So this first cable can stretch 2,000 millimeters. So this problem literally could be, you could have half this. You could have 1,000 millimeters. You could have 1 meter of slack, and this problem would still be kind of reasonable. It would be super sketchy, you know what I mean? Because you're taking something to 2.5% before the other rope hooks up. You know what I mean? But I mean, you could probably run data on a brand new cable and then stretch it in a machine, and if it says it can stretch up to 30%, because I think cables can, I mean, even a solid steel specimen can stretch 30%. It necks down and then breaks. But steel cables, I think they should be able to hit a huge percent, because I mean, they're cables. They're braided and they're woven, and at a certain point they do, you're pulling on strands of steel for sure, and then those strands of steel will neck down and break. But yeah, that's the take-home message, is that when you're working within that, you know, if you're hitting up to that max strain or change in length per length. Well, that's every material. That's just a tiny amount. You know what I mean? Let's do it for steel. Steel would be 0.002, and 0.002, and shoot, more time on the clock. Yeah, for steel, you couldn't even draw this to scale. I mean, because if you have 0.002, and then you could stretch it up to 0.5, or how was 0.05? Oh, no, it could be to scale. So you got, let's say this is 0.001, and you're going to go from 1 to 50. You know what I mean? So you would have a graph like this, 1, 2, 3, 4, 5, and maybe not even that far. But yeah, and you'd have 0.05 here, 0.01, and you would have, and you divvy this up 10 times. 5, and then 1, 2. So you'd have 0.02. So this graph for a chunk of steel would be all the way up to 58,000 pounds right there. Here would be your line. See how steep as hell that is? And then here's your elastoplastic. This is how far it could stretch. Comparatively, this change in length is potatoes compared to this elastic change in length before crap actually does break. But like I said, you could have something funky go on, and this could break at 1% for all we know. But it can break up to, and this is 5%. And steel, sky's the limit. It could go up to 20 to 30%. That would be pretty, you know, it can happen. So there you go. You can't talk enough about how these small change in lengths just past the elastic range are not a huge deal as long as you have something to back it up. But in this scenario, if you put more than 50,000 newtons in this cable, well, you're just going to stretch and break, and you're probably not even going to see it stretch. I mean, you're not going to see this cable meet its elastic. You're just going to know based on the properties of the cable. But the second you pass the strength of both cables combined, see you later, and that weight's hitting the ground. But yeah, that's what the graph looks like. Slopes the same. For that 25 millimeters, that's when both are actually doing stuff together. But after that, well, is this slope still a little bit higher? Because no, you're getting no more juice. You've already juiced this one out. Like I said, it's holding that much weight, but it can't hold anything more. Like once the first cable gets there, it can't hold anything more. So then the second cable. That was the take-home message of this. That's probably why it's 2-star. Anyway, that was a good one. Hell yeah. And it didn't break the bank time-wise. We learned a lot. So thanks for joining me. And guess what? That's a video.